Hey guys, Mr. Betts here. Let's take a look at a function that we can actually find the Maclaurin series for in a different way. We saw in another video that this is in the form of the sum of a geometric series, so we can find the Maclaurin series for this not using the traditional Maclaurin series formula. However, I do want to use the traditional Maclaurin series formula to show you that the geometric series way works. And then we're also going to find the interval of convergence for that series. So first thing I'm going to do here is I'm going to rewrite the function as 1 minus x to the negative 1. That's going to make taking derivatives easier. So first derivative is going to be negative 1 minus x to the negative 2. And then with the chain rule, we have to multiply by negative 1, so that actually makes that a positive 1. Then the second derivative is going to be negative 2, 1 minus x to the negative 3, and then chain rule multiplying by the derivative of 1 minus x, that's going to make that a positive 2. Third derivative, we're going to have negative 3 times 2 is negative 6 times 1 minus x to the negative 4, and then chain rule multiply by negative 1. One more here. I think this will be enough to establish a pattern. So this is going to be negative 24, 1 minus x to the negative 5th. And then that is going to keep going. Sorry, we have to multiply that by negative 1 also. I do want to point out that we got this by doing 2 times 1. We got this by doing 2 times 1 times 3, and then we multiplied by 4, and then the next one we're going to multiply by 5. And so it turns out that each of those coefficients is the factorial for the number of derivatives that we've done. So if I want to generalize this, which is going to be something we want to do if we can, this is going to be n factorial times 1 minus x to the negative n plus 1. So some version of that. So if we then evaluate this, since we're doing a Maclaurin series, we're centered at x equals 0. We want the value of the function at 0. So plugging 0 into the function, we're going to get 1. The first derivative at 0 is going to be we're plugging it in to the first derivative, we get 1 also. Second derivative at 0, we're going to have 2 over 1 to the third power, which is going to be 2. Third derivative is going to be the 6. Fourth derivative at 0 is going to be the 24. And then the nth derivative is going to be, evaluated at 0 is going to be n factorial. All right, and again, by finding the nth derivative, we can generalize this then. So the Maclaurin polynomial, and I'm going to squeeze this over. I didn't plan my spacing here very well, but I'm going to squeeze it over here. So I'm going to call this, say, m of x. Remember, the nth term in a Maclaurin polynomial is going to be the nth derivative evaluated at the center divided by n factorial times x to the nth power. So for the 0th term, we're going to have just the function evaluated at 0, which is 1. Then the first degree term, when n is 1, we're going to have 1 times x to the first power divided by 1 factorial. For the next one, we're going to have the second derivative, so 2, divided by 2 factorial times x to the second power. Then when n is 3, we're going to have 6 divided by 3 factorial times x to the third power. Then we're going to have 24 over 4 factorial times x to the fourth power. And then if we continue on here, the nth term is going to be n factorial over n factorial times x to the nth power, and so on. So cleaning this up a little bit, we get a function that we've already seen for this which is 1 plus x. These cancel, these cancel, these cancel, these cancel. So we get that geometric series that we saw before. Now, I want to remind you that when we write a Maclaurin series or a Taylor series for a function, it doesn't converge for all values of x necessarily. It's possible that it does. We saw that it does with the sine function. But let's go ahead and do the ratio test on that Maclaurin polynomial and see what the interval of convergence looks like. So we had our Maclaurin polynomial is 1 plus x squared, and so on. And what's going to be useful here for the ratio test is going to be that nth term. So remember, for the ratio test, our ratio, we're looking at the limit as n approaches infinity of the n plus first term, which is going to be x to the n plus 1, over the nth term, which is x to the n. And we have one more x on top than on the bottom. So this is just going to equal the absolute value of x. And the ratio test says that the series is going to converge if that ratio is less than 1. So absolute value of x is less than 1 is the same thing as -1 is less than x is less than +1. Now, we're not quite done. We do need to check what happens at the endpoints, because it's possible that we'll have convergence at -1 or at 1, because remember, the ratio test is inconclusive at those endpoints. So when x equals 1, then our series is going to be, just plugging 1 in for x here, the series is going to be 1 plus 1 plus 1 plus 1 plus 1 forever. So that is a divergent series. I think it's obvious that it diverges, because 1 plus 1 plus 1 infinitely many times is an infinite sum. So we will not include x equals 1 in our interval. At the other endpoint, we've got x equals -1. So plugging -1 in for x, we're going to have 1 minus 1. So this is going to be a -1 here. And then the x squared is going to be a plus 1. The x cubed is going to be a -1. X to the fourth is going to be a +1. And this is just going to alternate. So looking at our partial sums here, this does not go to infinity, but our partial sums here, our first partial sum is 0. Our first partial sum is 1. Our next partial sum is 0. Then when we add on 1, we get to 1 again. Then we subtract 1 and we get back to 0. So looking at our partial sums, these are not growing without bound, but they are not approaching a particular value. So at x equals -1, we get a divergent series because the partial sums oscillate. So what that means is we don't include either endpoint. And so this Maclaurin series for 1 over 1 minus x only converges for x values between -1 and 1, which is actually the same conclusion we got when we did the same thing looking at this as a geometric series.